Okay, great to see people today, and hopefully more will join online here. So uh, I had this is really the first session where we're getting into the substance of the course and begin our journey towards understanding the concepts of sheaves and co-sheaves and supporting concepts such as from algebraic topology, such as homology, cohomology, and basic concepts of topology, etc. Um, so uh, in this session, we're going to talk about the material that I asked you to review, which consisted of sort of three broadly different components. Number one was a video, which sort of gave a glimpse of sheaves in action in a particular context, and gave the flavor of where we're going. Secondly, I asked you to review the introduction to this book, Sheaf Theory Through Examples by Rosiak, that serves as our textbook. And that also included a bit of a glimpse of a example involving recognizing characters, right, from images and from sensors, each of which picked up only a portion of these characters, but where they could be the information from different images, some of which overlapped, could be put together to piece together a picture of the broader letter that was represented and an understanding of what letter that was. So that was the introduction to this book. And then finally, there were several subchapters of this book. And in the chapter one of the book that I asked you to go through, particularly in I believe it was subsections 1.1 and 1.2. So those provided rather different glimpses of where we're going. The latter part was much more focused on remembering some of the basics of category theory, right? Recalling or introducing, for some of us, some of the core ideas in category theory and introducing us to some examples of categories. Whereas two of the components, the video and the introduction, were giving us a bit of a glimpse of where we're going. So I wanted to discuss this, but want to give primacy to the voices of those here, and actually to encourage those of us who are newer to this material and categories to be able to make sure we can address their needs. So first of all, any overall reaction to this material?
Very feels very abstract right now,
Uh-huh.
but I'm hopeful that it will become clearer as time goes on.
Yeah, it definitely has an abstraction barrier to it, which is why it's hard for people to understand it when it's presented purely in abstract terms. The reason we chose this book, Sheaf Theory Through Examples, was that it's filled with examples of applications of this. And you did see two applications, albeit in brief, from the introduction and the video. And all of those had some sort of topological space depicted. They had maps between different areas of the topological space that reflected their relationship to one another. So you might have, to show it in a most basic form, maybe something like this might be some small region, this might be some region of space, maybe or sub age and some age range here. And then this might be the union of these two places. So if A and B are places, let's say, or periods of time, right? Maybe these are different periods of time. This is the, so different intervals of time. This will be the overlap between those intervals. So maybe this is, we have a scale of time. This is 0. Maybe this one reflects times from, let's say, 1 to 3 here. So this will capture data from 1 to 3, time 1 to time 3. This is time here. Right. Turn this one here. And maybe A captures along that same timeline, this is time as well, this period of time from 0 to 1, and these two are not the same. This one is a different time window than this, but they have some overlap, right? This overlap is between, so this is 0, 1, 2, 0, 1, 2, 3. You would think, just at a common sense level, whatever's depicted here needs to be at once sort of consistent with what's in this region and what's in this region here. So there's these maps that reflect the structure of the topological space. This space has this place A, or time period, time window A, time window B, and then a time window that's the overlap between those two. And this lies within this. For those who are more familiar with the categorical terms, this is actually a monomorphism, meaning this lies within that. It's a sub-piece of this. This is a monomorphism. This is a sub-piece. Those who haven't encountered this before, this is a little bit akin to an injective function. So it's suggesting this lies within it. It's picking out certain points within this. So this is a sub-piece. These are also monomorphisms. They're sort of also, this is a sub-piece of this. This is a sub-piece. So this is the topology. This is talking about the relationship of these things, and it forms a topological space associated with it. But it also implies something about the consistency of data. If we start, all of these examples involved assigning data. So not only the topology here, but assigning data to particular places on these so-called open sets. These are the open sets of the topology. I'm oversimplifying some things, but the idea is that we assign data on these things, and that's called data. The fact that we assign data to this, we have data associated with this, is the stalk associated with this, STALK. We're talking about sheaves, and this is kind of, think of data sticking up here for this. So there's some data over this here. There's some data over this here, some data over this. And this data tells us something about this data because of this relationship, because this is a sub-piece of that. This is a sub-piece of that. It's sort of, given this, you could restrict it down to this. This piece here can get restricted down to that. some of you may have encountered the notion of restriction in the past, like if we have sine of x, that's a function that over some real line that varies, right? Over some real line, and so on. But if we restrict it to a certain window, we could talk about sine x between time 1 and time 2. And that's a certain window on this. Like I've been trying to laugh at something like that. Here where the idea is the fact that this is included in here gives some restriction, means that there's a subpiece of this data that must be found here, the data for that. They're not independent of each other. If this is a piece of that, then the data for this has to be a piece of that data. And this goes back the other way. Given this waveform, we can restrict down to this piece. I don't know if that is helpful, but this was a piece of all of the presentations in the book. These were sort of images, and there was overlap in images, and what was seen in any one image would be reflected in the overlap, and it needed to be consistent from what this image showed and this one, here. And that allowed us to deduce something about the whole letter. But it also had to do with these restriction maps don't have to be just purely sort of taking a subpiece. Sometimes they're more complex things, like relating this to the terms with which this measures it. So I don't know if that's helpful, but that was a commonality. And the idea here is we need to reason about data that's in this and understand the ways in which it is consistent or inconsistent with some topology, some relationship between areas of a space, whether in time or space or other things. So I don't know if that's helpful to articulate these different examples, some commonalities in these different examples, but I did want to bring that out. But other things, additional comments. Those are good comments, Jeff, and we will try to make it more concrete. So that's a good call for us, and I appreciate that feedback. Any additional sort of reactions to those materials?
Compared to the geometrical space, the topological space has some notion of different meaning from the geometrical space. For example, for notion like distance. For myself, it's really ambiguity. To compare the geometrical space with the topological space, some notions that we define in the geometry like distance.
Right.
It's not clear in
well, yeah, so this is a good question. And what we'll see as the semester goes on is that there are commonly, so if you are starting, there are times where we don't start with a geometrical space. We start instead with some sort of logical structure of the situation. So maybe we're dealing with data at different levels of aggregation concerning a population, right? Data that's aggregated up to the level of the whole population, data that's specified for different subgroups of age groups, data that's specified for particular age groups, and we want to make sure there's consistency between them. So if you total up one way, you get the same result you total up another way. Or to use an example I drew on last time, if you have data broken down by regions of Saskatchewan, and then for Saskatchewan as a whole, and you have data for a particular region and particular set of age groups, and then you have other data that's broken down for different age groups across Saskatchewan as a whole, and then again data we have for the whole province. If you aggregate up either way, if you aggregate up over age, you should get the same result for the total number of people who got COVID in the last week as if you add up over regions and then get a total. Those should be the same, right? Yeah. And so that's an example where it's not geometrically based. There are many cases where it is geometrically based. And even if you want to consider geography, spatial dimensions there, and you want to really consider it in some sort of geometric context, there are a wide variety of needs for doing that and for turning those into topologies that reflect that space. And I want to particularly highlight a tool that Jeff and Ujay would have encountered before called the Vietoris-Rips complex. And as part of that, what you're doing is you're connecting up things that lie within a certain radius of one another. Okay. So if you have two things that lie within a certain radius, they're connected. But more than this, you will generally seek to take into account not just edges between two things. Maybe you have three things that are nearby enough that they have an area of overlap. Some area that lies within distance r, some radius of each of them, some area in which all three are nearby, then that would form a triangle called a two-simplex, where you have point X, point Y, and point Z in geometric space, and you have some ball around each of them. There's some ball around each of them, and some ball around each of them. And there could be some area which is in, I'll do it like this, just so you can see it. This is an area that it's in all three of them. And so here we might represent that as a topologically in what's called our simplicial complex as having X, Y, and Z. And this represents the area of overlap. This surface represents the area of overlap for each of them. YZ would represent this overlap between Y and Z. That's kind of this region. XZ would represent the overlap between X and Z. Oh, sorry, yeah, Y and Z. Yeah. X and Z, which would be, sort of this region and so on. I don't know if that's helpful, but often we take a geometric picture and we turn it into a topological picture that reflects proximity according to some criteria. And the idea here is topology focuses on the connections between things, or the connectivity between things. And often that's what you're interested in understanding from location. It's not location. It's not all the details of location in of itself, but what it means about proximity in terms of interaction, in terms of having some relationship with one another, or some interconnection between them. So often we typically the route is to take a geometric picture, turn it into a topological picture that provides what's called a simplicial complex, which retains the essential properties of this. And one of the real findings that's really exciting from algebraic geometry, from topology, is that we can analyze the topological properties of what we abstract from the geometrical situation, and they will retain provable fidelity to. In other words, they will give the same results as if we had applied them geometrically.
You can say that is kind of abstraction from
It's abstraction, and the right abstraction to guarantee that properties that we would have deduced from the geometry are are found from this abstract representation. And this abstract representation allows for vastly more efficient and more computationally tractable representation. It's also what we call combinatorial because it's built up out of pieces. And by building it up out of pieces, we can describe it in a form that is very that allows for us to treat it with a computer more easily. Yeah. So very often we will take a geometric picture and abstract it into a topological picture that captures with a certain level of guarantee the underlying space. And in fact, the UMAP protocol, which Jeff and Ujay have used, does exactly that. I mean, it takes a geometric picture of things, boils it down into a simplicial picture, but in a more sophisticated way, in a way that takes into account that you might need to account for incomplete sampling of the space, etc. I won't get into it. Yeah, I don't know if that's helpful. Yeah. But the geometry is often of core interest, and in fact, I referred you to this video by Michael Robinson, this professor who does work sort of spanning engineering and algebraic topology. And most of his examples are spatial. But they're boiled down into simplicial representations because of the guarantees that are assured. We can then manipulate them efficiently. And we can manipulate them critically. I don't want to tip our hand too much, but we can turn this into linear algebra. And we can reason about it with linear algebra. And we can process it with linear algebra. And we can use linear algebra to find features of the underlying space that it abstracted. I don't know if that's helpful. Yeah. But other reactions. So this is some broad components. I want to be attentive to Jeff's needs because it's the first time he's seen category theory. And I want to see, it wouldn't be bad for all of us to have some refreshers on this. But Jeff, do you want to talk about anything that you found challenging in that area?
In category?
Yeah. Or that you're puzzled by, or is there anything that I could help address?
I mean, the answer is going to be yes, but I can't put my finger on anything specific.
Okay. So maybe it would be helpful to talk about some of the major things that were discussed there. So there was a definition of a category, which involved, you may remember, objects, which we treat as basically like dots. We don't get into what they represent. We don't go into them. The attention is not what's inside the objects. The attention is the connection between objects. So we have objects, we have morphisms, and we're going to have the ability to compose any two end-to-end morphisms. So if we have objects like this, every object has what sort of morphism? And identity morphism, an ID morphism, right? And it's typically not drawn because it's always there. So we have the convention of not drawing things that are implied to clean up the diagram. But we can have morphisms. So if we have a morphism F from let's say object, let's call it, don't worry about this stuff below here, X, Y, Z. Okay, now I'm in trouble. W. if we have morphism F from X to Y and another one G from Y to Z, we're guaranteed to have a morphism from where to where?
Okay, well, W, I believe it's one.
Oh, from W, yeah. X from Y to W. Thank you. Thank you. From X to W, that's right. Yeah. We have a morphism, and we can write this in two ways. One way is G after F. So we write this with a sort of open dot, G after F. Another way that it's very commonly written is F fat semicolon G, meaning F and then G. Sometimes you even see it without the being too fat. You could see it like, oh no. You could see it just a regular symbol. F and then G. You could write it either way. And notice that this must exist for any two end-to-end arrows. Now, we think of these X, Y, and W often as, it's sometimes useful to think of these as types of things. Because like arrows are specific to the type of thing. So, you know, maybe this is Boolean or something like that. And this is like, well, G wouldn't go from this. Okay, from a Boolean, you can. I'm thinking about something that would give a double, whether or not, if it's true, gives not a number. If it's false, it gives 0 or something like that. Okay, not a number. It's probably a bad example, but there might also be morphisms from Boolean to Boolean, like not, right? But the point is, the types of morphisms you'd have for an int, like over here, maybe X is int, would be different here. Now, I'm thinking about the category Hask or the pseudo category Hask. But the point is, in a more general way, we think about these. It doesn't have to be programming language types, but these are different types of things, and therefore the operations that apply, the morphisms out, are different depending on what sort of thing you have, right? And that's commonly the case. So we can compose any two pair of end-to-end arrows. There must be a composition, which is generally not drawn. But that's not all. There are certain extra guarantees, extra axioms that apply. What are those axioms? Does anyone remember?
Like commutativity, transitivity.
So you've got some good ideas there. The key things are what's called unitality. What is unitality? So transitivity is like this one that I've actually drawn already. Like you compose something from X to Y with something from Y to W, you get something from X to W. That's kind of like saying if A is less than B and B is less than C, then A is less than C. It's very much tied in with transitivity. But unitality has to be, means that if I have ID X, ID sub X, and then I follow it by F, what is that equal to? F. But F also equals F followed by ID Y on the other side, right? So if I have F and then I do ID Y, I just stay. It's not just I stay here. Nothing. It's just exactly the same as F. It's purely the same. This is called unitality. It guarantees that the unit morphisms do nothing. There may be self morphisms on Y that are not identity. Like not, because we're Boolean. But identity for Boolean will be, if it's true, it's what? True. If it's false, it's false. Right? And if I said, if X were integer and I said, is a certain integer prime, and then I followed it by identity on bool, it would just be like saying, is it prime? It's nothing else. It's composition here would give the same result. This is prime. So this is called unitality. So this is one property offered with any category. Any category. This applies to, an infinite number of categories. But we find the same thing. So there are categories of matrices. What do you think unitality represents for matrices? What's unitality? Yeah, identity matrix, multiplying an identity matrix. So we'd be having identity matrix involved then. If we have a category where we have self-morphisms, like if we have a category that's representing a poset where a link from X to Y means X is less than or equal to Y, what would the ID morphisms be here? This were a poset, so if arrows here mean not maps, but X, it's relations. X is less than or equal to Y. What would a unit morphism be for X?
X.
Less than or equal to X.
Yeah.
Exactly. Right? So Jeff's idea earlier directly applies transitivity here. If this is a pre-order, and if this were a category now where F represents a relation less than or equal to, F and then G is transitivity, right? Just like I said, if F means X is less than or equal to Y, and G means Y is less than or equal to W, then composition is transitivity. X is less than W, right? By the way, there's only in a pre-order, it's a so-called a flat category or a thin category, because we don't need to write what it is. It's just there, it exists or not. Like there's no F, there's no multiple possible things. So either it exists or it doesn't. If it doesn't, it's not less than or equal to. If it does, it is. But here, identity, as we said, was so identity less than or equal to for X would mean X is less than or equal to X. So if I apply that with transitivity, that's what composition deals with. Unitality deals with composition. Composition here is transitivity. If I said X is less than or equal to X, I want to consider it the transitive property X is less than or equal to X together with the property X is less than or equal to Y. What's the implication? X then is less than or equal to Y. It's the same thing. It doesn't add any information. Do you see this? So here, it just leaves it unchanged. Do you see that? Here? And similarly, if I said X is less than or equal to Y and Y is less than or equal to Y, and I apply transitivity, I get X is less than or equal to Y, which is exactly what I had. So it doesn't affect it, right? We could apply this for many categories. The same reasoning. But what's the other axiom besides unitality? Associativity. And what does associativity say? Jeff was thinking in the right direction, but it's turns out it's not conjugativity, it's associativity. So it says basically the order of the composition doesn't matter, or one pithy way to say it is, it doesn't matter where the parentheses are. So, and therefore you don't have to put parentheses at all. This is actually very nice. So if you have F and then G and then H, it doesn't matter if you have F and then G and then H, because this, you could compose this, right? And then that, or if you do it F composed with the composition of G and H, it doesn't matter. It's all the same. This is probably something we take for granted in certain contexts. Let me give you an example. In computer science, if we concatenate a string, one string with another, we could think of that as involving sort of a composition. So maybe let me compose a string in two ways. I'm going to have the string foo, the string bar, and the string baz. Okay, those are my three strings. Okay. Does it matter what order I do these concatenations? Like if I do foo and then bar, what do I get? Foo bar, right? Right? And then if I concatenate that with, maybe I'll use phosphate, you know what I mean? With baz, is that the same as doing foo with the concatenation of bar and baz? Yes. It's the same. This is associative. Same thing with arrays. If you have arrays of elements, if you stick one array after the other, it's associative. Because there's categories. It's actually very beautiful. There's categories there. And in fact, for those who are interested in, you get something that is very closely related to the free monoid. But in any case, the point is a lot of operations we deal with in the world are associative. Non-associativity is messy. Now, we'll see that we'll come back to this with a more mature way because of understanding this, because there are places where these aren't exactly the same, but they're isomorphic, meaning if you have this, you have the same information, you can produce this. If you have this, you can produce that. They're only different in silly little ways that don't reflect any difference in information. They're the same thing, just they look a little bit different, and we can convert between them when we treat them as essentially equivalent. But I'm talking right now for associativity, these things equal each other. That's what associativity says. These two equal each other. Okay. This is categories. So we have these two axioms, unitality and associativity. And then we have objects, morphisms, and this ability to compose. So I'm going to say something which it took me a while to understand. Categories are about capturing structure. The form of a category captures structure of the situation. The primary place we capture that structure is in the rules for composition. What composed with what yields what. That is how we capture the essential logic of the situation. And the most important things for categories are their morphisms and the rules of composition associated with them. You know, it get together with the axioms. It's not the objects. So I don't know if you made it through to the final part of the reading, but there's And actually, I'm not even sure. No. It's the reading for next time. There's a nice section on no objects where the author actually notes that categories can be defined with no objects. Or really one object, and that's all. And the essential thing is the power of categories comes from morphisms and composition in light of these sets. Okay. So I don't know if that helps at all, but those are some components of this. Now, one other thing that was introduced was this notion of a commutative diagram. And I'm going to draw that like this. So if we have F, and then we have G here, right? And we have H. Oops. B. H is here. Maybe these are objects X. Maybe this is W, X, Y, Z. This property associated with associativity means that if we go this way and then to Z via composing it with this, it's the same as going, sorry, this way and this, these two compose together. And we say that these two paths, they're commute. And sometimes we'll draw a square or a triangle for that. This would be an example of a commuting triangle here, for example, where if you go here and here, it's the same as taking this up to there. So no matter what you go up this or up here, it's the same. You go either way, you'll get the path is the same to this. So if you're starting here, you go to W to this morphism or this way and this way. The two ways of getting from X to W are the same, and that's why we put a check mark. Sometimes people write a little, like a little circle, and it sort of commutes. It's the same either way. I guess technically you do it in the other direction.
In this situation, where should you put a check mark?
Well, it's a good question. I think I would redraw it.
Mathematical understand, okay.
I would redraw it. So we probably would do something. I'd have to think about this, but we might say, okay, so if you go X and then Y, and then you were to go to Z like this. Excuse me, this is sorry, W, this should be Y. So this would now be F and then G. And then H has got to be the same as W going to X with F. And X goes to Z with G and then H, right? And this commutes, right? Right?
Okay.
It works out.
It works out. works out. It doesn't look too bad, right? This kind of captures the essential picture, maybe in a way that communicates these are sort of side cuts. This maybe looks a little bit. There's a lot packed
We
in.
want to draw the arrow
Yeah.
for X to Y.
Yeah. Yeah, I mean, it's kind of nice if you could draw each of the more of this in a more granular. Whereas this is kind of lumping a couple things together, but this is the essence of the situation, right? It's asking if you take the composition of this and then 8, is that the same as first doing this and then composing? I mean, this does capture the essence. This is a commuting dot. If there's nothing shown, generally you shouldn't assume it commutes. Sometimes people show something and the text makes clear it commutes, but generally you don't want to assume every path commutes. So generally that's not true. Can you give me a category where every path commutes? There are categories where every path commutes. In fact, I'd use their name, 2 names for them. I gave 2 equivalent names a few minutes ago. A category for what's called a pre-order. So here, if we have this is related to a partially ordered set too, but if we have like X is less than W, something like that, and Y is less than, maybe we'll do it like, yeah, maybe we'll do it with a little example. So here's, yeah.
I'm gonna rotate the camera to get the.
Oh, thank you. Okay. Think like that. Did that?
Okay, yeah, that's good.
Okay. So if we have like cats. Dogs.
Cats scared of dogs, dogs scared of the.
Well, no, I was gonna do like, these are in mammals. Right? These are mammals. And then like. Okay, this is gonna be weird. Yeah, this is actually quite uninteresting. But mammals are part of. I should know. Animals. Right? This is a pre-order. This is part of that. This is part of that. Or you could say this is less than or equal to that in some abstract sense. This is less than or equal to that. It's kind of within it. This is within it. This is within it. Or this is a that. This is a that. If there's multiple paths up from something, then I mean, maybe I could do something like this. This would be kind of a little bit weird, but canids, this is like includes all dogs, right? But it also includes jackals and African wild dogs and wolves and coyotes and and if that's in mammals, there's only one path up here. It's not like this gives a different path than that. This is the same. So this automatically commutes. There's only one path up to here. This is why we call it a thin category. Any paths from X to Y, there can be multiple paths, but they all must be the same. Like the composition of this is that. It's just dogs are canids, canids are mammals, therefore dogs are mammals. So pre-orders are a thin category. In other words, between any 2 objects, there's either 0 or 1 morphism. There's not multiple ones. So let me give you another. I'm going to give you another thin category. That's kind of fun. This is from Eugenia Chang. This is from Michael Robinson's things, but here's another category that's thin. Another pre-order. I think you may know where I'm going. Mackie may know where I'm going with this. It's possible that Jeff does. One divides two evenly. One divides three. Does two divide three? Three divides six. Does two divide six evenly? Hmm. If I put 5 here, what does it need to be connected to? One. Hmm. And what does it divide?
30.
It divides 30.
Mm.
Yes, I mean, does 6 divide 30? Yes. Does 2? Does 3? Yes, they all do. Let's not draw it because it's going to be composed of other things. What other things can we put here? Like, for example, what else might involve 2 and 5? 10. Oops, it's a 10, not a 16. Sorry, this is butchered. My handwriting is bad enough by itself, and then to have it like way stretched is okay. Here we go. Here we go. Like this, right? How about 2 and 3? We already have. How about 3 and 5? What do we need? 15. Hmm. Does 2 divide 15? What's that? No. No. Okay. Okay. Good. Anything else we need? No. So here, what does an arrow mean? I told you, it means
Is a factor of.
it's a factor of divides. Here, are there multiple paths, say from 3 to 30? Yeah, this one, but they're not different. They all commute. There's only either 1 or 0 arrows between any two things, right? So this is a category. I mean, there's a category. Yeah. It's a category associated with this. So, 2 up to 30, depending if you go this way or this way, yes, it's the same thing. 2 divides 30. It's not like there's 2 different ways. Well, it's not like there's 2 totally different ways of dividing 30. It can divide it through 10 and through 6, but at the end of the day, what this classifies is, does it divide 30? This is what's called a pre-order. Pre-order. This is a pre-order. Mm-hmm. And it's a good reminder that just as was said in the book, sometimes with categories, we're dealing with kind of sets with structure. We're dealing with things that are basically sets with added information in them. Other times, these arrows are not functions. I appealed up here, like if this is int, if I was appealing to the pseudo category Haskell. If this is int and this is bool, maybe f is prime, right? It says for each integer whether or not it's prime number. And maybe there's another one from x to y that might be is odd, right? Another one from x to y, from int to bool, that might be is even. All of those take an int and they return a bool. You get that idea? So they're kind of function-like, right? They're like mathematical
For
functions.
every element of one, there's a matching element for.
Yeah. Yeah, and maps. ints to bool.
Not necessarily one-to-one, could be one-to-many.
That's right.
Many-to-one.
That's right. And if you have a bool, you could take it's not, right? Or you could just, all of them, any int has an identity function on ints that given an int returns the same thing. Any bool has an identity function on bool, given bool takes the same thing. Any double has an identity function on it. There are things that turn ints into doubles, maybe take the square root, right? So in here we have lots of functions between these, and there's there are different types, but it's very it's very profuse in terms of the number of morphisms, right? Here, our arrows are not functions. They're not maps. They are about relationships. They're relations, but they're not mapping one thing to another. Here we talk about it mapping, right? Int maps to bool, right? That's a very intuitive notion from set theory. Int get a bool, right? Here the functions here morphisms are not functions, they're not maps, they're relation. Here, okay, this is divides by, this is a, right? This is like is a. This is like divides. But there's another one that we referred to that actually has a total order on natural numbers, where we might have this. It's in the book, but we might have this. 0, here's 1, here's an object called 2, here's an object called 3, blah, blah, blah. Don't worry about what's inside the objects. The objects are dots. This is 4, blah, blah, blah. But here, what does an arrow mean? Less than or equal to. Less than or equal to. So, per Jeff's comment, is there transitivity? If 0 is less than or equal to 1 and 1 is less than or equal to 2, does that mean 0 is less than or equal to 2? Yeah, so that's composition. Composition is transitivity. You get that? But again, it's a thin category. This is thin, this is thin, this is thin. So morphisms mean different things. They mean something different in different categories. Here it's a relation. But they all obey the rules of category. What is unitality? So you tell me. So what's an identity morphism here? What's an identity morphism for, well, what's an identity morphism for this diagram? Is a
Cat is a cat, dog.
a cat is a cat, a dog is a dog, right? What's an identity morphism for this one? Every number divides itself. What's an identity morphism for this one here? This total order. Any number is less than or equal to itself. Right? Notice we have to be very careful. We didn't have equal would be all sorts of trouble, because then it wouldn't obey the rules of the category. This will obey the rules of the category, right? What's identity morphism in this one? Or if this were int, this were bool, what's it? We said it before. Yeah, it's an identity function, right? From ints to ints, it just returns the same thing, right? Are we good with this? Okay. Okay. What if we should? Well, I want to take more questions. I realize we're over time, we're in office hours now, but I want to take more questions. I'm tempted to talk about something else, but I don't want to freak people out. So, we can leave monoids and categories of the categories of the higher these categories, like categories of vector spaces or categories of monoids or whatever. We can leave those to
Monoid group, ring, field.
yeah, we can talk about those later, or monoids of pre-orders, etc. But, okay, so what other questions could I answer? Associativity with string. What other questions could I answer here?
For the last example you have of the vertical.
Yeah. Yeah.
Is the category represented by like the undrawable infinite line or like a subset of that line could be a category?
Well, a subset of the line could. Well, okay, so that's, yeah, it's a subset of the line. Let's think about it. So suppose this only went up to 3. Could that be a category? Yes, it can. Yes, it can. Why do I say that? Well, let's think about it. Are there objects? Are there morphisms between such objects? Yes. Does every object have an identity morphism? Yeah. We don't draw it, but yes, 1 is less than or equal to 1, 2 is less than or equal to 2, 3 is less than or equal to 3. Does it obey unitality? Yeah. If you say 0 is less than or equal to 0 and 0 is less than or equal to 1, it implies 0 is less than or equal to 1. The 0 is less than or equal to 0 doesn't add any new information, right? To the transitivity, in the context of transitivity. Is it associative? So if we say 0 is less than or equal to 1 and 1 is less than or equal to 2, which means 0 is less than or equal to 2, and now we say 2 is less than or equal to 3. Does that give the same thing as saying 1 is less than or equal to 2, 2 is less than or equal to 3, therefore 1 is less than or equal to 3, and now we say 0 is less than or equal to 1. Yes, both give the same implication, 0 is less than or equal to 3. So it's a category, yes, this would be a category, a happy category. Each non-category is unhappy in its own unhappy way. Each category is happy in the same basic happy way. To adapt Tolstoy. And categories are happy things because they're beautiful structure. And it's the same structure again and again and again in all these areas of mathematics. It's the same picture. It's the same tune. They're all whistling the same tune. The tune of happiness. Okay. So other questions though. That was a good question.
Like in David Spivak's book, he said category theory is unified language.
All areas. Yeah.
Things.
Yeah. I mean, it's reached almost all areas of mathematics, maybe all now. It's basically this universal language. But critically, for our purposes in our lab, one of the real attractions is you can take a categorical description, therefore, and bring together multiple types of mathematics, like the mathematics of continuous systems with the mathematics of discrete transitions and state charts, and weave them together, the mathematics of networks, and weave those in, because it's all category. It's all just category. And they all speak the same lingo. Yeah. Other questions, though, or other comments or queries or challenges?
Can the category have more than one morphism or just one?
Oh, yeah, it can have many. You mean between 2 pairs of objects?
Yeah.
Yeah, it can have great question. Great question. A pre-order category, these sort of things, can only have one morphism because that's why it's thin. It's either 0 or 1 morphism between any 2 objects. 0 or 1. That's why it's thin. It's also called flat. Flat. By contrast, in this category, okay, we have ints and rules. Can there be more than one way to like have a predicate on ints, like. Yeah, that we could ask if ints are prime. That would be one of these morphisms, right? Is each int prime, right? That could be is prime, might be one, right? There might be another. Is odd. Right? There might be another. Is even. There might be another. Is colapse. Is it a collapse number? Another is Fibonacci number, is in Fibonacci sequence or something like that, right? There could be all of these different ones, you know, is it greater than 100? Is it greater than 0? Oh, well, greater than 0, yeah. Is it positive? Is it negative? Yeah, there's all these here. So set is particularly prolific in terms of functions, and Hask with having types is more restricted, but it's still prolific. There's like zillions of functions here because there's very little structure within this, within each of these int and bools and so on. But this is a good place to say that, probably a good place to introduce the notion that there's a category set. And set, or its more tame relative, thin set. And maybe we'll talk about thin set, because maybe it's easier to grasp. So what are the objects in thin set? Often when we talk about a category, we say it's a category, its objects are X, its morphisms are Y. So what are the objects in thin set? They're finite sets. So any one of these is a set. So this might be the set of smiley face and 0. Right? This might be the set of elephant, right? With an elephant and a flower. Okay. This might be a set of 0, 5, 10, right? And there's all these sets, but they have to be finite in size. They're all finite in size in fits. All these different sets. Okay, so those are the objects. Are there a lot of them? Yeah, there's an awful lot of them. There's an infinite number of objects. But they're all finite in size individually. They all have a finite number of elements if you care. But for our purposes, there they are, many of them. What are the morphisms between them? Remember, our real attention, the real insights come from their functions. These are functions from one thing to another, right? So maybe it maps the elephant. So maybe there's a function from this set to this set, and it maps the elephant to happy, and it maps the flower also to happy. Are we okay with that? No one objects? Okay. There's a function, right, between those sets, right? And maybe there's a function from elephant to 0, 5, 10, which represents the closest number of tons that it weighs, and metric tons. And the elephant maps to 5, and the flower maps to 0. Right? These are functions. So for a given function, it maps each and every element of its domain. So a given function has a domain, that's where it's coming from, and a range where it's going to, or its codomain, we call it more commonly. It's codomain. So this function has a domain of the set of elephant and flower, and a codomain of the set 0, 5, 10. And here to be a function, it has to, its job in life is for each and everything in its domain, where it comes from, what it's mapping from which it maps, it has to pick out something in its codomain. So it turns elephant, it maps elephant to 0. It maps flower, sorry, elephant to 5. This flower to 0.
So we're choosing these mappings, like it's not that necessarily every set has to have a map to every other set. We're choosing which mappings we.
Yeah, some sets won't have maps to others. In fact, there's a key set of foremost importance. There's a key set of foremost importance, in part because there's not a lot of things that map to it. There's one thing that maps to it, and that's all. What is that thing of key importance? Can anyone say? It's a key set. It's a very distinguished set. It's an empty set. And I'll put it in, I know there's many ways to show it, but I'll put it in. It's the empty set. Huh? By the way, I want to emphasize these functions are morphic. That's what I'm saying, right? The objects are sets, finite sets. These morphisms are functions. So those are morphisms, right? Between any two objects, there can be a lot of morphisms. There can be another one which, instead of classifying their metric tons, it classifies the size of the number of height in meters of the element. The closest number here for the number of heights in meters. Flower again will go to 0. Go to 10 meters. So what? Not 10 meters. It's also 5. Okay. So be the actually the same number one, not a problem. Okay. So here's the empty set. What sets map to the empty set? Remember, the job of a function, in order to do its job in life, it has a responsibility. It has to map each and everything in its domain, where it comes from, to some particular value in its codomain, where it goes to. So, which sets have a map to empty set?
Empty set itself. Okay?
Only empty set. Yeah. Empty set has a map to itself. Nothing else has a map to it. Okay, but there's something actually even equally, arguably more interesting than that. What morphisms does empty set have out of it? What does empty set map to?
I want to say nothing.
Does it map to nothing?
I think could map to everything, right?
It's either nothing or everything.
So let's remember I emphasized the meaning of a function has to, for everything in its domain, each and everything in its domain, it has to pick out something in its codomain. So let's consider whether there's a map from the empty set to the set consisting of elephant and flower. Does that? If I posit that there's a function, what would to understand whether there's a function, I have to ask, is there something that for every one of these things in the empty set, every one of the elements in the empty set, it picks out a response to? Yes, because it's vacuous. There's nothing to do. It's kind of empty. It doesn't have to do anything.
Yes.
It satisfies it trivially. How many functions are there from it to the elephant and flower? There's just one. Is there one to the smiley face and 0? Yes. Is there one from it to 0, 5, 10? Yes. Is there one to this set, whatever it is? Yes, yes. There's exactly one to every other set. Every other set. Is there one to itself? Yes. Because it never runs into a problem because there's nothing to map. If it had something to map, it would run into a problem. Like, I can't map it to anything. This is sometimes called the absurd function. Yes, it has nothing to do, so yes, it exists to itself. Okay, so this is actually called, this is a very special object. These are each object set. This object is called a initial object. Or sometimes it's, what's the other term for it? There's another term for final, terminal and final, but initial and I should remember, I can't remember. Yeah, I think there's sometimes might call it something. Anyway, it's an initial object. Initials, the most common. Let me ask this. Do you see initial objects in this category? Not all categories have initial objects. But is there a number, even a number shown right now, that divides everything
One
evenly? One. One will actually divide everything. Will it divide itself? Yeah. One is initial. This is an initial object in this category. This is an initial object in this category. Does this category have an initial object? If the objects are natural numbers, does this category have an initial object? Zero. Let me ask this. If this were not natural numbers, but integers, would it have an initial object? No, because there's no integer that is small. There's no limit to the lower side of the integer. So there's always going to be some, no matter what integer you pick, there's going to be one below it, right? Now, if you pick integers union a thing called minus infinity, yeah, minus infinity would be initial.
So in that case, animal is a terminal, yeah, because,
This is the terminal.
yeah.
Well,
Yes.
right now it's the terminal object, yeah, if we decide it. So our categories, this is actually our first example of what's called the universal construction. Meaning it's universal, it's like of all the things, it's the most quintessential in some regard. It's the one, in this case, that's unique because it's canonical, it's distinguished by the fact that it is maps out of it to each and every other object. That's what distinguishes it. It so happens that this doesn't have any links into it, except from itself. Same thing is true for one, but the thing that makes it initial is it has exactly one to every other object. Does this have? I don't show it here explicitly, but is there a map from 1 to 30? Yes, we just don't draw it because it's implied by the composition. Hmm? Well, sometimes I draw like that. Yes, everyone. So, yeah.
Relation with animals, initial object.
There's no, I can't think of an initial object for animal. I mean, not all categories have initial objects. There's actually quite a few categories that don't. Some categories don't. Like the category with integers and less than or something. That is a category. Actually, objects are integers. Morphisms are less than or equal to. You can compose, that's transitivity. There's unitality, with each object has an identimorphism, less than or equal to itself. There's no initial object for it. Is there a terminal object? There? Yeah.
Could we consider integers with it's like a morphism, perhaps like less than or equal to the absolute value of? In which case there would be an initial.
Yeah, something. Yeah.
Is that a morphism?
Yeah. I see. I think I see what you're saying. You're asking like, is the absolute value of this number less than or equal to the absolute value of another? Yeah, we could define that, in which case it would have an initial object. Yeah. 0 will be initial. Now, one thing I tried to emphasize in all these examples is that categories are very diverse. Morphisms sometimes mean maps, but sometimes they can, for example, indicate relation. Does something divide? Indicate one thing is a whatever, right? This thing is less than or equal to that. So these kind of distinguish objects, etc. I also noted that set has, and by extension has, is particularly profuse, particularly prolific in terms of having functions between things. And the reason is sets have very little structure. Basically, essentially no structure. They're just collections of elements. But it's going to get a lot more interesting when we start having categories of things that have structure. Categories of things that have some sort of internal structure. Maybe they're as simple as a category of preorders, where each object is a preorder and maps from it from one to another, or they're maps from one preorder to another that preserve the structure, meaning they're monotonic maps. That's what we're going to talk about a little bit next time. Okay, is this? I think we should go a little bit slow. I'm going to actually suggest that we cut back a little bit on the reading for next time so we can talk about this some more, because it seems that this is a good discussion. And I want to make sure that particularly Jeff's questions are addressed and that we have a chance to really engage with this material, because it's going to suit us very well. But I will say that when we have things that are maps, if our objects start having structure, that will constrain what the maps. If each of these objects were a graph, and these would be graph homomorphisms, things that turn one graph into another in a way that honors the structure. One goes to another means this target graph has, in some ways, has similar structure to this one. It may be coarser representation. Maybe this one collapses some things, this one distinguishes. But now they're homomorphisms. They're ways of relating that capture the structure. If these were preorders, these would be things that honor that structure by being monotonic. If these were vector spaces, this is a vector space, these would be linear transformations between them that are nice transformations between them. If these were topological spaces, these would be smooth maps between them that honors that structure. And those would be for maps. There's still these categories where that's not an issue. There's thing categories, etc. But we will be seeing that, and there the number of morphisms will be many less than in set, because the morphisms are not as willy-nilly. They can't scramble things. In set, you could have any old morphisms from the elephant to another set. I mean, set with the elephant, not function. There's no order, not like, the morphism has to be bigger for the elephant than it is for the flower, or it has to smell better for the flower than for the elephant. No. It's nothing like that at all. There's just, these are bags of elements and they can be mapped willy-nilly because there's nothing to preserve in terms of structure. They're just bags of things. We're going to be going to things where these have structure of some sort and the morphisms have to honor that structure. And that's going to be the basis for a lot of what we're going to be exploring within categories more generally. So for those who have seen this before, this is a causal loop diagram, and this is a causal loop diagram. this might map this causal loop diagram to this one in a way that it can embed it in this, or it can collapse certain nodes here to be the same nodes here, but it's basically has similar structure here as to it there, and that's why there's a homomorphism, it's a sort of map that sort of captures that structure. So we're going to be seeing that a lot going forward. With set, we don't really get that much. With Hask, we don't really get it because this is, even if these are ends, there could be any subset of them, and how it maps one end doesn't constrain how it maps another. If it had to be monotonic, if instead of larger have to be mapped to larger doubles, that would be now getting into sort of homomorphisms. Okay, it has to be a monotonic map, and that's what we'll be able to see. So, okay, are we okay with this? Let's let me just check. Okay. What the category of don't freak them out again. Don't freak them out. Don't freak them out. You have to be careful, one step at a time. One step at a time. These things are powerful concepts, and it's worth mulling over them before going on to
In
advance.
some way, it's kind of nice to know that the space exists and that's where we will be going.
Oh, yeah.
As opposed to like.
Okay.
Space.
Okay, that's good. I will say that if that category of sets seems Wild West to you, the Finn set, because it's got all these elephants mixed with flowers, mixed with, rocks and, bowls and broken sticks, or like, don't worry about this much, because most of the time with Finn set, we're actually going to deal with what's called the skeleton of Finn set. You know the skeleton of Finn set? That's a pretty nice category. Skeleton of Finn set is much more well behaved. What it means is that we only have one object, skeleton of Finn set. Here, we only have one object of each size. Size 0. Size 1. Distinguish what it is. It could be a flower, it could be. It just, there's only one of them, one object. One object of size 2. Something, something. One object of size 3. Got it. This is one object of size 4. And then we can do, and that's really cool. Let me ask this, is this still initial here? Is that still initial? Yeah, it's still initial. How many maps are there from this to each other object? Just one. Just one, that's why it's initial. I mean, it's exactly one map to every object. Okay, how many maps are there? I'm not laughing. I'm laughing because this is actually really a deep thing, and it's a beautiful thing, and I'm delighted to show it to you. How many maps are there from this object where you only have one thing to map? How many maps are there from this? How many sort of sets are there? Functions, rather. Functions from this to this. Two. It either can map this one to the first or to the second. So there's two of them, right? This one maps to the first. How many maps are there from this one, singleton, to this one? 3.
Combinatoric.
So in total is 2 times 3 is 6.
Well, okay, but so that's true, but one step at a time. How many are there to something that is 4? 4 things. A tuple of size 4, whatever's in there. There's only one of
For 1 to 4 is 4.
There's 4 maps. So the maps from this object one-to-one correspondence with the size of the set. If you tell me any object, you say, if Jeff says, I'm not gonna tell you which object it is. And I can ask you one question, I'd ask, okay, how many maps are there from this thing to it? And if you told me there's 99, I'd say you're telling me about 90. It unique. That's what. So this is what we do all the time. This is why in category theory, if you've ever wondered, we all the time have this, but this just counts the number of things in this. Now, how many maps are there to this object from anything else? How many maps are there from it to itself? One. How many are there from this guy to that? Here it is. One. Good. How many maps are there from this guy with two elements in it, two things in it, this set, to a single thing? Well, for each and every one, it has to pick one to map to. Guess how many choices there are? Only one. So there's only one function mapping. For this guy, which does it map to the only choice? Which guy does this map to the only choice? There's only one function.
We're getting into the numbers are permutations and combinations in one direction or the other.
Well, no, from this, how many are there to this? Just one. So this map, remember, initial has one map, one morphism to every object. Terminal object has one map to it from every other object. So this is the terminal object. And commonly we write the initial object as 0 in a category, if it exists. And the initial object is 1. That's why I wrote 1. This is the initial object. Initial object. Everything has one map to it. Exactly one map to it. Does this have any initial object? Sorry, any initial object? Yes. 0. Does it have a terminal object? No. Does this have a terminal object? Well, for the one shown here, it would be 3. If we included 4 here, it would not evenly divided. But if we've only allowed these ones, yeah, 30 is total. Does set have a terminal object? Yes. Set, well, fin set has a terminal. Yes. And set, does it have a terminal object? Well, it has a set of isomorphic terminal objects of size 1. One flower, one elephant, one rock, one bowl, one person, one dog, one cat, one salamander, one hedgehog, echidna, one planet, right? Those are all isomorphic, so those would be considered terminal isomorphic. They're all anyway. Terminal. Okay. Haskell has a terminal object, and it's called unit. It's like there's only one possible bet. Terminal objects here in Haskell are types, int, bool, double, whatever. This is a type. That's what. Other questions? This is delightful. I love talking about this stuff. What's puzzling? What's puzzling?
I'm thinking about like the number of mappings. Like we started with one from each of those.
That's right.
Thinking about like
The combinatory.
how many mappings are there, and
oh yeah.
Part of me is now thinking about its size of set raised to power of size of set.
What? Okay.
Because you can map both of these ones to this one.
Yeah,
Both
it's
of these
true.
ones to that one.
It's true, so like. Okay, so this is a good question, very good question, very good question, bit of a subtle. So. I claim. That there are. I claim. That there's exactly one morphism from the terminal object to any other object. Hmm? And that's the definition. Terminal object. Oh, sorry. One morphism to the terminal object from any other object. One morphism from the initial object to any other object, right? Okay. So here's a question. So does 0 have a morphism to 1 to the single thing? It does. It does right there, right? And that's why it's in it. Why we call it 0. Does 1, think about composition here, have how many morphisms does 1? Target. How many does it have to the distinguished set with 2 elements? 2 morphisms, right? So you might think that there are then, for each of those, that you could compose it with this map from 0 and get 2 morphisms from 0 to this, but that's not. There's only 1 morphism from 0 to this. They're not different, they're the same. Now, why is that? Well, it's not the case that all morphisms, all paths are necessarily distinct. Here, like the paths from 1 to 30, they were all the same morphism. You could get there multiple ways, but they all commute. These commute as well. So if you go from, I'll draw it down here, but if you go from 0 for this guy here, if you go from 0 to 1, and then 1 has 2 morphisms into 2. One is this very nice property. Not only is it terminal, every one that's 1 to it, but it also has this nice property that the number of morphisms from it in bin set are set. Everything else is in 1-to-1 correspondence with those things. And generally, that's true for a broad set of categories of sets we structure. But here we have 2 morphisms. What I'm saying is that either way you go, if we call this F and we call this G, that if we draw the commuting square, 0, and let's call this 8. Okay. Draw it. 0. Okay, 0 to H, yeah. And then we do, okay, fine. Right. And then we do G. And we go, so this is 1. This is 2, right? I'm just sort of transcribing. And then watch this. I could draw it like this too. This is a fine way to draw it. It's the same object. Same object. H. And then this is F. This square commutes. That G after H is the same as F after H. There's only 1. There's only 1 from 0 to 2. This holds here. There's only 1 from 0 to 2. These 2 have to be hit. And you may ask, why is that? Oh, how could they be the same? Why is that? That's weird. No, it ain't so weird. Because this is a map. This composition of H, of G after H, or of F after G, what's its domain? What's, sorry? Yeah, the domain of H and then G, this goes from 0 to 2, right? And how many things are there to do from 0? How many possibilities are there? It's just that there's one vacuous one. It's like there's nothing to do. It's kind of a vacuous thing. So H after H and then G, or H and then F, both have nothing to do. So yeah, there's only one way to do it. There's only one way to do nothing.
Nothing is nothing.
What's that?
Nothing is nothing.
Yeah, nothing is nothing. There's nothing to do. There's nothing that has to be done. It's just, it's the same, both of these, H after G and F, sorry, H and then G and H and then F, both are from 0 to 2. There's, nothing to do, right? To do. And the same function, right? The same one. Zeros, a little bit odd. Now, we're going to deal with tons of categories where there are zeros, zero objects, initial objects, and ones, terminal objects. And very commonly, we will have this sort of feature where the terminal object pick out the number of possibilities in a given set, which is beautiful. It's a beautiful thing. Is there an initial object for the causal loop diagrams? Is there an initial causal loop diagram? So your morphisms are homomorphisms between causal loop diagrams. The answer is yes, there's an initial one. What is it? Empty. Yeah, empty one. Is there a
But empty.
is there a terminal causal loop diagram? Because it would, yeah, I mean, this is getting to more advanced stuff. I
Well,
don't
the
want to
causal
scare
loop
you.
diagram is defined as they have a kind of an edge.
Yeah, exactly.
But
It-
empty doesn't follow the definition there.
Right.
But the empty causal loop, empty,
Well, no, it can't. It just, there's 0 vertices in it. But there can't be one because terminal, it would need a morphism in from any one of it. And again, I don't want to get Jeff worried about this right now, but all the links would have to go somewhere.
yeah,
And you need it to at least have like a self loop.
yeah,
That any link can be mapped into that self loop. Then an object with a self loop, like an edge to itself, that's plus, and another one that's minus.
yes.
So that like these things, yeah, those would be, it would allow homomorphisms from any other one to it. It's terminal cause. So it's like all variables. Yeah. Okay. What other things are bothering you? You look unsettled, Jeff.
Got me thinking about, because we've so far presented categories that are
Yeah.
sets with the morphisms being relations.
Yeah.
Oh,
Well,
sorry, sorry, that's not what I mean. Sets with like mappings, that's what I mean.
with mappings, yep,
And then
with
we have
functions,
categories
with functions.
Essentially, each object is a singular entity with a relation.
Yeah,
Yeah.
that's true.
Is there
Good.
an overlap between those? Can we?
Yeah, I see what you're saying. Yeah. Because you're saying here, I think I see what you're saying, and you're right to be wondering about it. Like here we have kind of, these are like sets. There might be type sets, but they're sets. Over there, where you were dealing with sort of finite sets, right? and these are like the skeleton, like the bare bones finite sets, like the minimum where we consider all that are isomorphic to each other, all that have the same number of things to be the same. We just collapse them, right? Hmm? And I think what you're saying is, then there are these ones where we have like particular numbers, they're not sets. Yeah, I mean, I could have, okay, so this is gonna, maybe this will be disconcerting, maybe it will be appealing. So I said like fin set and set are defined as categories where the objects are sets or finite set, and the morphisms are functional between them. Could we have a category where the objects are, let's say, finite sets? Maybe. Yeah, finite sets. Maybe we want to deal with fin set because the skeleton of fin set. We'll deal with fin set. Could we have where the objects are finite sets of finite sets, but the morphisms are cardinality relations, like is one smaller than another in terms of number of elements? Can we have that? Same objects, but different morphisms. We have that. Would that make sense? Would it obey a category? Well, we have object. Finite sets. Well, we could do it in set. Yeah, sure, we could do it here. Morphisms are like there's a morphism from set A to set B if the cardinality, the size of A is less than or equal to, no, I said equal to the size of B. So I'm saying, imagine that we have more. Is that sensible as a category? First of all, there are objects and there are morphisms. Okay. Is there a composition? If set A has an arrow to set B and set B to set C, does that mean there's guaranteed to be one from zero, or sorry, set A to set C? Yes, because if set A has a size less than set B, and set B has a size less than or equal to, and set B has a size less than or equal to set C, then A has a size less than or equal to size C, to that of set C, right? Does that make sense? Is there a unit morphism for every object? Well, let's think about it. Well, so say we have an object of size 2. Is there a unit morphism from it to itself? Yeah, less than or equal to itself. It's less than or equal to itself in size. Is there composition? Yes, I think I said that. There's composition, it's transitivity, it's size. Is it associative? Yes. If A is less than equal to B in size, and B is less than equal to C in size, then A is less than equal to C in size, and then if we consider C is less than equal to D in size, then A is less than equal to D, and that gives the same result as if we first considered it A is less than B is less than or equal to C in size, and C is less than or equal to D in size. Therefore, B is less than or equal to C to D in size, and now we want to combine that with A is less than or equal to B in size. Yeah, in both cases, they yield the conclusion A is less the relation that A is less than or equal to D in size. So it's a category, and they are the objects of sets. We have sort of sort of pre-order category. Pre-order category with sets. Yeah, that works perfectly fine. Perfectly fine. Could we have it with sets as the objects, and we say there's a morphism from one set to another, A to B, if the number of objects in A evenly divides the number of objects in B. We have that. Oh, why not? Does meet rules for category? Yeah, meets the rules for category. A is the size of A, less evenly divides the size of B, and the size of B evenly divides the size of C, then A size of A evenly divides the size of C. Works fine. The size of A evenly divides the size of A. Yeah. Yeah. So we can have that. Mm-hmm. Mm-hmm. Mm-hmm.
Well, you can say that category of set is a P of a category, a schema category, yes. When we talk about this
The category of what?
category of set is P sheets from a schema category. Yes, you can say any category of set has a schema category.
Mm.
And when we talk about the different category over category of set, like creations or other category, what's happening in the schema category?
Well, okay, let's wait to talk about that till Jeff is along and gets exposed to schemas, and there's a beautiful story there. But let's wait for that, especially because we're at 55 past, and I've got to get onto a call in 5 minutes. But that's an interesting question. There's going to be I think a nice story for that we'll talk about. But